Hey there and welcome to this video. In the following I'll be doing a paper implementation of diffusion models. Diffusion models are extremely popular right now and are being applied to almost every single task which involves some kind of generation. The most popular tasks they are being applied to at the moment is image generation, and you have probably heard a lot from models like DALL-E 2, Stable Diffusion or ImageGen. While all of them differ in their exact approach, they all have the same fundamental underlying technique, and we are going to implement this technique in this video. Before we're getting started though, in order to fully understand the video and the implementation, you should have a basic understanding of the theory behind diffusion models. If you are not familiar with it, you can take a look at my explanation video which I made recently, or take a look at all the other incredible resources out there. Okay, so what is this video going to be exactly about? At first we are going to do a basic implementation of diffusion models in PyTorch. This will consist of coding all the tools for the diffusion process, so noising images, sampling images and so on. Of course we will also cover implementing the famous UNet architecture as well as the training loop. Then we will train this model on some dataset and look at the results. After that you have a great starting point to apply diffusion models to your own datasets. Furthermore, over time there were so many improvements to diffusion models, making them faster or better. This is why I want to talk about a few and also implement them. The two main things I want to talk about are classifier-free guidance and exponential moving average. Don't worry if you don't know what it is, I'll explain it later. However, these improvements will require us to rewrite some of the existing code to work conditionally, since classifier-free guidance only works with labels and our first implementation will be unconditionally. And of course we're also going to train this and look at the results afterwards. After that you should have a pretty neat understanding of how to implement diffusion models, and maybe you can extend them even further with your own ideas. So before getting into the coding, if you need a short refresher about diffusion models, let past me give you a recap. Diffusion models are generative models which became super popular in recent times for beating GANs on image synthesis. The main idea behind diffusion models is that we have two processes. The first one is easy. We just gradually apply noise to an image over a lot of steps until the image has turned into complete noise. The cool thing is that we can also do this in one single step, which saves us a lot of compute and time. Now, the goal of the reverse process is that we learn how to remove noise from an image. But as we saw, we don't instantly try to remove all of the noise, we do it step by step. That's just easier for the model to learn. For that, we have a neural network which takes in an image and the current time step t and predicts the image at t-1. Well, to be more specific, we saw that we can reformulate it so that we only predict the noise in the image. Then we can subtract the predicted noise from the image at time t and get the image at t-1. We will do this over and over again until we arrive at t=0. And if the neural network was trained well, we now have an image which could occur in our training data. Alright, after this short reminder, let's dive into the code. Okay, so you can see I've created a new project and got what will be our main file up here. At first I will just do the casual imports for all the things that we need. The first thing that we'll code, and this will be the most important thing out of all, are the diffusion tools. And as I said earlier, this will cover setting up the noising schedule, a function for noising images and also for sampling images. And I'm just going to put all of this in one single class called diffusion. The main parameters will be for the number of sampling steps, the lower and upper end for beta, and the image size. And the default parameters you see here will also be the ones that we are going to use in all training runs. I'm setting the number of time steps to 1000 as proposed in the first papers. Then I also use the same values for the betas, and the image size will be 64 by 64. I'm using a fairly small resolution here because I'm only training this on my RTX 3090 and higher resolutions would take much longer. And also going with the flow of recent state-of-the-art models, you probably would rather train separate upsamplers to get to higher resolutions instead of just training one big base model. But that just as a side note. In this video we will also just be using the linear beta schedule as proposed in the first papers. If you want to use the cosine schedule proposed by OpenAI, it should be very simple to change though. Okay, so these will be our betas, and remember the alphas that were introduced, which are basically just for making the formulas look thin and nice in our algorithms. We'll define these here. The alphas will simply be 1 minus beta, and then we also need the cumulative products of the alphas. You'll see in a second how exactly we are going to use them, so don't worry if you don't remember that. Okay, so the first really important function that we'll need is to noise images. And if you remember from the explanation video, there were two options to do that. The first would be to iteratively add noise over and over again until we are at our desired step. But there was also this great insight that we can just do it in one single step. And of course that's exactly what we will be doing because it's much faster. You can see the formula on the screen, and basically all we do is to take the square root of our alpha's head and then also the square root of 1 minus alpha head. At last we will also need some random noise and plug all of it into the formula, and voila, this function is ready. Another helpful function that we need is one which can sample some time steps, because we need that in algorithm 1 for the training. And we can just do that in a single one-liner like this. Okay, so now let's take care of the sampling. Our sampling function will take in the model which we will use for sampling and the number of images we want to sample. At first we are going to set it to evaluation mode and wrap the following context in a torch.nograd. Generally everything that we are doing here will follow algorithm 2 from the DDPM paper I also talked about in the explanation video. You see, the first thing that I'm doing here is to create our initial images by sampling from a normal distribution using torch.randn. And now here comes the big loop going over all 1000 time steps in a reversed order, starting with the highest and going until 1. The first thing in the loop is creating the time steps by just creating a tensor of length n with the current time step. And after that I will feed that into the model together with the current images. The last thing we will need is noise, which we add and scale with the variance later. But remember, we only need noise for the time steps greater than 1, because in the last iteration we don't want to add it because it would just make our final outcome worse. In that case, I will just set the noise to be 0. And now for the final operation, in each iteration we will alter our images and remove a little bit of noise by making use of the formula that you see in the algorithm. And that's already all there is in the main sample loop. After that we will set the model back to training and clip the output to be in the valid range of -1 and 1. The +1 and the division by 2 is just for bringing the values back to the range of 0 and 1, which we will further multiply by 255 to bring them into the valid pixel range, and then change their data type for saving them later. And that's it. Easy, right? Until now we've treated the model in the sampling loop as a black box, which just takes in the noised images and time steps. So let's start coding the UNet now. I switched over to the modules.py file and defined the basic construct for the UNet. It will take in the input and output channels, which will be both 3 since we are working with RGB images. But you can also feel free to maybe try it with just black and white images. The next argument is the dimension of the time step embedding, which you will see in a minute. As you probably know, a UNet has an encoder, a bottleneck and a decoder. Since our model will be very easy and straightforward, I won't be making separate modules for all the 3 subcomponents and just put all the actual modules here. But you'll see which parts belong to the encoder, decoder and bottleneck. Also, for now I'll just put all the names of the modules here to give you a brief overview what the UNet will consist of, and afterwards we'll code each of the modules themselves. At first we'll start with a double conv, which as the name suggests is just a wrapper for 2 convolutional layers. Again, you'll see the details soon. After that we'll put 3 downsample blocks, each followed by a self-attention block. The arguments to the downsample block are just the input and output channels, and for the self-attention block the first argument is the channel dimension and the second one is the current image resolution. Each downsample block will reduce the size by 2, so going from 64 to 32 to 16 to 8. After that we have the bottleneck, which just consists of a bunch of convolutional layers, and after that we go straight into the decoder part, which is basically the reverse of the encoder and consists of 3 upsampling blocks, again each followed by a self-attention block. And at last we are projecting back to the output channel dimension by using a normal conv layer. The forward pass is pretty straightforward too. We'll take as input the noised images and the time steps. As mentioned earlier, the time steps will only be a tensor with the integer time step values in it. But here comes the interesting thing now. Instead of giving these to our model in their plain form, we'll make it easier for the model and encode them. Most diffusion papers just use the sinusoidal embedding, and we are also going to go with that. I'll put some resources in the description if you want to know more about them, but due to time reasons we'll just take them as given. The only thing to note is that we provide the explicit dimension which we want to encode them into. So to give you an example, this is what it looks like if we have the following time tensor, and encode it using the sinusoidal embedding. Keep that in mind because we'll use that knowledge in some of the modules. Okay, cool, and the rest of the forward function is literally the same that we talked about in the init method. So nothing new here, except that you can see that the upsampling blocks take in the skip connections from the encoder too. We'll see in a minute how they will be combined. But yeah, that's already all there is for the abstract layout for the UNet. Let's now take a look how all the modules work in detail. The first thing that we'll look at is the double conv module. It is really just a normal convolution block as you have it in many other architectures and consists of a 2D convolution followed by a group norm and a GLO activation, and then another convolution and a group norm. Furthermore, there's also the possibility to add a residual connection by providing the residual keyword with true. Okay, next up is the downsample block. Its main component consists of a max pool to reduce the size by half, followed by 2 double convs. It's as easy as that. But there's one more really important thing, and that is the embedding layer you see down here. Remember that we encode time steps to a certain dimension. However, since most blocks differ in terms of their hidden dimension from the time step embedding, we'll make use of a linear projection to bring the time embedding to the proper dimension. And you see this just consists of a GLO activation followed by a linear layer going from the time embedding to the hidden dimension. In the forward pass, you see that we first feed the images through the convolutional block and project the time embedding accordingly, and then just add both together and return. That's it. Okay, now let's move to the upsample block, and you can see that it's basically exactly the same for the init method, except that we have an upsample operation instead of a max pooling as in a downsampling block. And the main difference in the forward pass is just that we also take in the skip connection, which comes from the encoder, and after upsampling the normal X, we concatenate it with the skip connection and feed it through the convolutional block. And then at the end we also add the time embedding to it again. Last but not least, we have the self-attention layer, and this is really just a completely normal attention block as you probably know it from transformers. This can be seen good in the forward pass here. We first have a pre-layer norm, which is being followed by a multi-head attention. Then we add the skip connection and pass it through the feed forward layer, which also consists of a layer norm and 2 linear layers which are separated by a GLO activation. The first and last operations, which you can see here, are just for bringing the images into the right shape, by first flattening them and then bringing the channel axis as the last dimension, such that the attention can work properly. And voila, that's it for the model part. Once again, you see that it's quite easy and not as hard as you might have expected it from Diffusion Models, right? Okay, we're almost done already. We only need to write the training loop now. But before that, I will write a few helper functions that will be useful in a training loop. The first method is just for plotting images, and the second is just for saving them. The next function is for preparing the data. I just have some basic transforms here which will resize and crop the images and then convert them to a tensor and normalize them to be between -1 and 1. After that I define a dataset where I just use the built-in image folder and then return the data loader. The last function you see here is just for setting up the folders for saving the model and the results. Awesome, let's go to the training loop. At first I just define all the necessary things such as the data loader, the model, the optimizer, the loss, our diffusion class, which we have written before, and the logger-to-logger training stats. Now we can start the actual training loop. We'll iterate over all our epochs and then during each epoch run over the entire dataset. Everything that will come now follows exactly algorithm 1 from the DDPM paper. Our data loader will provide us with the images, then we sample random time steps in a range between 1 and 1000, and after that we'll noise the images accordingly based on the time steps using the noise images function from the diffusion class. This will also return the noise which was used since we need that in the loss calculation. Then all we do is just feeding our noised images to a model which predicts the noise in the images, and then we take the mean squared error between the actual noise and the predicted noise. And then it's just the usual optimizer stuff where we first call 0grad, then backward the loss, and then take an optimization step. And that's already all there is for the main training loop. It's extremely simple, right? I will just add 2 more lines for logging, and after each epoch we'll sample some images and log them too, and save the model. At this point I just want to re-emphasize that diffusion models are generally pretty easy to implement, especially if you think back to the explanation video and how math heavy that was. Another thing I want to mention is that when you look at other diffusion model implementations, especially the really popular ones, you'll see that their code is very different and much harder to understand regarding the sampling process. That's why they are still using the lower bound formulation, which I personally don't understand, since the first DDPM papers clearly show that this is not necessary anymore. My only guess is that it makes sense for a few further modifications to diffusion models, such as learned variants where we do need the lower bound again. But yeah, maybe if anybody of you knows why that is done, feel free to share it in the comments. However, I think for understanding diffusion models, this implementation is much better suited, since you can really focus on what was shown in the paper and don't get confused by 1000 lines of additional code which you didn't expect and have no idea where it is coming from. So yeah, I guess it's time for training this model now and see where we get. I'll be using a small landscape dataset for this unconditional training. It has about 4000 images in it. I will train it for 500 epochs using a batch size of 12 and an image size of 64 by 64. I will train on a GPU and use a constant learning rate. And I guess with that being said, let's start the training. So this has been training now for 500 epochs and you can see some results on screen here. I personally like them a lot and I guess we can definitely say that it is able to generate landscapes. Here are also some more results from different epochs and it's very interesting to see how these evolve over time until they become realistic landscapes. Awesome. So now, as promised earlier, we'll also look at two improvements for diffusion models, which are classifier-free guidance and exponential moving average. Classifier-free guidance, or CFG, can be used to improve generations if we train with classes. It can help to avoid posterior collapse, which simply means that the model ignores the conditional information and just generates any image. An example would be if we wanted to generate an airplane, but the model would just generate an arbitrary class such as a car. And CFG can help to avoid that, and often also results in better sampling outcomes. But you already heard that we need classes for that, and that's why we will need to adapt our current code a little bit. We'll be using Cypher 10 for that, which has 10 classes. Originally this dataset came out in 32 by 32 resolution, but I'm using an upscaled version at 64 by 64. Let's first talk about the model changes. There are plenty ways to condition a model, but one of the easiest to implement and one that works reasonably well is to just add conditional information somewhere inside of the model to some intermediate result. In diffusion models we have an easy time since we already have the time step as a condition, so we could just add the conditional information of the label to that. And again here, instead of adding them in their plain form being a number in the range of 0 to 9 for the 10 different classes, we'll also use an embedding for them, but this time the model can learn it itself. For that we extend our model by a num classes argument and create a label embedding for all classes. And note that this will have the same number of dimensions as the time embedding. And in the forward pass, literally the only thing that we're changing is that if labels are provided, we'll add their embedding to the time step embedding. And that's already all the changes for the model. Easy, right? Going over to our training code, we'll now expect labels to also come from our data loader, and during training we'll also pass them to the model. Now our code works for class conditions. Cool. Okay, so how does classifier-free guidance work? During training for like 10% of the time, we'll train unconditionally. That way the model learns to do both, conditional and unconditional sampling. And during sampling, we'll sample also both ways, but linearly interpolate away from the unconditional sample towards the conditional one. And we'll do that in every iteration. I'll put the paper for CFG in the description so you can read it more carefully if you're interested. So the only thing we change in the training loop is that we set the labels to none for 10% of the time, which will result in that the model only uses the time step and no class information. Okay, and then we also need to modify the sampling loop. You can see the exact formula for CFG here on screen proposed in the paper. It's basically a linear interpolation between the conditional and unconditional predicted noise. This is why we can use torch lerp function, which does exactly that. So if the CFG scale is bigger than 0, meaning that we want to use CFG, we'll first sample unconditionally and then just do the interpolation. And that's all we need for enabling CFG. We'll do some comparisons later to see if it actually works better than training without it. The second improvement that we will implement is exponential moving average, or EMA. EMA is basically a way of enforcing a smoother training. It literally smooths the trajectory of the model updates. So if the training is really noisy and the direction of the optimization changes a lot, EMA can smooth this trajectory and lead to a more robust outcome, since it's not so susceptible to outliers in terms of model updates as the main model. EMA works by making a copy of the initial model weights and then updating these based on the moving average from the main model. The formula for updating a single weight using EMA looks like this. It's also an interpolation between the old weight and the new parameter, weighted by beta. Beta is usually around 0.99, which shows that the new weight only affects the EMA parameters a little bit, which prevents outliers to have a big effect. Let's move to the code and implement it. I'm just going to create a new class for that, which would take beta as an argument. We'll let the EMA updates start after a certain number of iterations to give the main model a quick warm-up. During the warm-up, we'll always just reset the EMA model parameters to the main ones. After the warm-up, we'll then always update the weights by iterating over all parameters and apply the formula I just showed you before. Cool, that's it for the EMA class. Let's put it into action in the training loop. We'll first define it here and create a copy of a model, and then the only thing we'll add here is to call the step EMA function after every model update. And that's already it. We'll also compare some sample from the EMA model versus the original model after the training to see its effects. Okay, then let's start the training on Cypher 10 with the new updated class conditional model, which uses EMA and CFG. I trained this now for 300 epochs, and you can see the results here on screen for the different classes. These are using the normal model and without using CFG. If we use the EMA model, you can already see a significant difference from just looking at it. On the other hand, if we only use CFG, then these are the results here. And in the bottom right corner, we have images sampled with both EMA and CFG. I guess that we can definitely say that EMA and CFG help and result in better generations, and there's not even a big trade-off that we need to encounter for getting better samples. But that's just looking visually at it. To show that it's actually better than the normal model, you could do some analytic calculations like FID or other stuff. But for time reasons, I won't be doing that here now. Alright, so this sums up the training of the conditional diffusion model with classifier-free guidance and EMA. You see that it's really not that hard, and all of this can be implemented in a couple lines of code. And yeah, that's it for this video where we implemented diffusion models from scratch in PyTorch. I really hope you enjoyed the video, and feel free to suggest other topics I should cover or things that can be improved. And also thank you for 1,000 subscribers. And yeah, with that being said, I wish you a nice day.